Imagine this. You take some liquid, you put it on a speaker cone, turn up the vibration. Boom. Not splashes, but perfect patterns.
Uh-huh. Mesmerizing ones.
Yeah. Stable, geometric shapes just appearing. It feels almost like magic. So for this deep dive, we're digging into Faraday waves. We want to figure out the physics, connect the dots between the liquid itself, like how thick it is, and how these incredible shapes actually form.
It's a really fascinating area, and, it's not new. Michael Faraday first wrote about this way back in 1831.
1831, wow.
Yeah, he noticed these little ripples, these patterns forming when a liquid gets shaken vertically, up and down, pretty quickly.
And the patterns you see, stripes, hexagons, whatever, they aren't just random noise, right?
Yep.
They're specific standing waves.
That's exactly it. They're surface standing waves, and they depend entirely on the shaking conditions, the frequency, the amplitude.
Okay, so what's the actual physics? If these patterns are stable, holding their shape, there must be some kind of cycle, some repeating forces.
There are. The core physics here, it's governed by something called a parametric oscillator.
Okay, parametric oscillator, let's pause there. How is that different from, say, just pushing a swing? Is it like a feedback thing?
Sort of. Think about a simple pendulum. Gravity is constant, right?
Right.
But here, in the frame of reference of the container that's shaking up and down, it's like gravity itself is oscillating. That changing parameter, the gravity, is what drives the system.
Ah, okay, so the environment is cycling.
Precisely. That's why sometimes you'll hear them called standing gravity waves.
Got it. And this leads to the really famous part, doesn't it? The subharmonic rule.
Yes. This is the key signature. The waves on the liquid surface oscillate at half the frequency you're shaking the container at.
Wait, exactly half.
Exactly half. That's the hallmark of parametric resonance. If you shake the container at, say, 40 hertz, the waves pop up at 20 hertz. The system finds stability by responding on every other cycle of the push.
That's wild.
It is. Now, of course, if you push it too hard, shake it too violently,
The patterns break down.
they do. Those nice, neat shapes dissolve, and you start getting, well, chaos. Researchers call it a fraction of spatiotemporal chaos. It just becomes unpredictable.
It's still amazing that simple up and down shaking creates such perfect order, like those stripes and squares. But the liquid itself must make a difference. Water versus oil, maybe?
Oh, absolutely. The fluid properties are critical. Viscosity, density, surface tension, they all matter.
So, like, water would behave differently than thick oil.
Definitely. Researchers see totally different results, different thresholds for when the waves appear, depending on whether they use low viscosity fluids like water or more viscous ones like different oils.
Okay.
And there was this really interesting finding with corn oil, actually.
Oh, yeah?
They observed that its viscosity, how thick it was, actually increased quite a bit after just 5 minutes of being shaken really intensely.
No way. So shaking it actually changed the oil itself.
It seems so. The idea is that the constant shearing, the stress from the shaking, might be rearranging the molecules inside the oil.
Wow. That makes studying it tricky.
It does. It shows how complex these nonlinear behaviors can be, even in something that seems simple. It adds another layer to the theory.
So, okay, this goes back to Faraday, 19th century. But you're saying it's still relevant. What's the 21st century angle here?
Oh, hugely relevant. Faraday waves are a very active research area because they give us a way to control fluids precisely without touching them.
Like for technology.
Exactly. Think industrial uses, like making spray cooling much more efficient. And maybe even more exciting is in biotech.
Biotech, yeah.
For things like making really tiny uniform droplets for delivering drugs exactly where they need to go, or even helping to assemble microscopic things like groups of cells for tissue engineering. They're using it with organoid cells.
So you can use these waves to build tiny structures.
In a sense, yes, to guide the assembly. And it's such a fundamental effect, they've even recently seen Faraday waves pop up in studies of quantum matter, Bose-Einstein condensates.
Okay, that's incredible. From a dish of shaking corn oil all the way to quantum physics. That connection is really something.
It really is. And when you look at how these wave patterns can shift, or even how a whole train of waves can sometimes collapse into just one single stable wave, a soliton near the resonant frequencies, it just shows how this very simple input, just shaking something up and down, can generate incredibly complex, but also predictable and frankly beautiful wave structures. It's deep.
It really is. Well, this fascinating deep dive was sponsored by embersilk.com. If you need AI education or integration solutions, Embersilk is the answer. Check them out at embersilk.com. And if you enjoyed this conversation and want more intellectually curious topics like this one, please do subscribe to The Deep Dive. And hey, leave us a 5-star review if you can. It really, really helps us out. Thanks for listening.